Welcome to Domain 3, Section 3.1, Types of AI. In this session, we will build a clear mental map of the whole field, how AI, machine learning, and deep learning nest together, the types of AI by function and by capability, the major model families, how machines actually learn, and the key terms every security professional should know. Why does this matter beyond the exam? You cannot secure or govern a technology you do not understand. Knowing the types of AI lets you ask the right questions about any system you encounter, judge what a model can and cannot do, and spot where its particular design creates risk. This is the vocabulary the rest of Domain 3 is built on. Let's start by untangling some words that often get muddled. Picture a set of nested circles. The widest is artificial intelligence, the broad goal of machines doing tasks that normally need human intelligence. Inside it sits machine learning, where systems learn patterns from data instead of being hand-coded. Inside that sits deep learning, which uses many layered networks to learn ever more abstract features. And generative AI lives within deep learning, creating brand new content from the patterns it has absorbed. With that map in mind, there are two ways to categorize AI: by what it can do functionally, and by how capable it is overall. The functional view gives 4 types, and the capability view gives 3. Let's take them in turn, because the exam expects you to know both lenses. The first 2 functional types are the simplest. Reactive machines respond to the current input with no memory of the past, like a reflex that fires the same way every time it is triggered. Limited memory systems go a step further by using recent data to inform decisions, much like a driver glancing at the last few seconds of road and traffic before changing lanes. The vast majority of today's AI sits in this limited memory category. The next 2 functional types are far more advanced and largely aspirational. Theory of mind describes a machine that could understand human emotions and intentions, in effect, reading the room and adjusting its behavior to people's mental states. We see only early, partial hints of this today. And self-aware AI, the final type, would possess consciousness of its own mind and feelings. This does not exist and remains purely theoretical. Now, the capability lens, starting with artificial narrow intelligence, or ANI, sometimes called weak AI, this is a system limited to one specific domain, like a tool that only translates languages or only sorts images. Despite the name, narrow AI is enormously useful and is essentially all the AI in use today. It performs its single task with great accuracy, but has no awareness or general understanding beyond that narrow lane. The next step up is artificial general intelligence, or AGI, a system that could handle any intellectual task a human can. To qualify, it would need broad capabilities like sensory perception, problem solving, natural language understanding, creativity, and social emotional engagement. Real progress is happening in areas like vision and language, but human-level common sense and fine motor skills remain out of reach, so AGI does not yet exist. Beyond even that lies artificial superintelligence, or ASI, a hypothetical stage where machine intelligence would surpass the best human minds across every field, solving problems and creating innovations beyond our current imagination. It is, for now, purely a concept. Let's move to the major model families, beginning with generative models. A landmark design here is the generative adversarial network, which pits 2 neural networks against each other. One network generates fake samples while the other tries to tell fakes from real, like a forger and an art authenticator locked in competition. As they train, both improve until the forger's output becomes so convincing the authenticator can no longer tell the difference, which is how these systems learn to produce strikingly realistic images, audio, and more. A fast-rising family is Agentic AI, the next evolution beyond simple assistance. An AI agent can make autonomous decisions and take actions to achieve a goal, such as keeping a process running efficiently. Its benefits include greater specialization on granular tasks, easy experimentation, and, thanks to stronger reasoning, fewer hallucinations than ordinary generative AI. But it still needs human oversight. because vague goals lead it badly astray. Another family is predictive models, which use historical data and machine learning to forecast future events and trends, spotting patterns in the past to anticipate what comes next. They power things like equipment failure, prediction and forecasting. The key risk is that decision makers must genuinely understand how a prediction was derived, so that choices rest on verifiable reasoning rather than blind faith. Now to the heart of it, machine learning, where machines learn from data using mathematical models. A crucial concept here is the label, which is the known answer a model is trained to predict. Labels are not always easy to get. Hand labeling millions of data points is slow and expensive. Some categories are genuinely ambiguous and need expert judgment, and in brand new domains there may be no known correct answer at all. This challenge shapes which learning approach you choose. There are three main learning paradigms, and the first is supervised learning, which trains on labeled data, like studying with an answer key. It splits into two tasks. Regression predicts a continuous number, such as forecasting next month's energy demand, and classification sorts items into categories, such as judging whether a piece of fruit in a photo is ripe or unripe. Variations like semi-supervised and self-supervised learning help when labels are scarce or costly. The second paradigm is unsupervised learning, which works on raw, unlabeled data with no answer key, finding hidden structure on its own. It does three main things: clustering groups similar items together, like sorting a music library by sound without being told the genres. Association rules uncover relationships between items. And dimensionality reduction simplifies data with many variables down to the few that matter most. Its main drawback is weak explainability, so a human in the loop is important. The third paradigm is reinforcement learning, where an agent learns by trial and error, earning rewards for good actions and penalties for bad ones. Imagine a robotic cleaner gradually discovering the most efficient path through a home by being rewarded for covering more floor. It suits autonomous control, like adaptive intrusion detection, but its independence makes safety and human oversight essential. Underpinning much of this are neural networks, collections of algorithms loosely inspired by the brain. A network has three kinds of layers: an input layer that receives data, one or more hidden layers where the real computation and learning happen, and an output layer that produces the result, rather like an assembly line transforming raw materials into a finished product. There are several types worth knowing. Feedforward networks pass information in one direction, suiting tasks like image recognition. Recurrent networks have loops that handle sequences, suiting language and speech. And convolutional networks specialize in grid-like data, such as images, detecting edges, textures, and objects. When a network has many layers, it becomes deep learning, which can extract features automatically. And an automated technique called neural architecture search can even help design the best network, though always with human oversight. Let's talk about algorithms, the step-by-step rules that power all of this. In machine learning, algorithms let models analyze data, find patterns, and make predictions, and each comes with hyperparameters, the dials you set before training to tune how it learns, such as the learning rate. Algorithms fall into classes matched to the learning paradigms. Supervised ones like linear and logistic regression, decision trees, support vector machines, and others. Unsupervised ones like clustering and principal component analysis. And reinforcement ones like Q-learning. Choosing the right class for the task matters as much as tuning it. And ensemble modeling, which combines several models, can improve accuracy and reduce the weaknesses of any single one. Finally, a handful of terms round out your vocabulary. A large language model is trained on huge amounts of text using a transformer architecture to understand and generate human-like language. A prompt is the input that triggers a generative system. And output quality depends heavily on how specific that prompt is. Foundation models are broadly trained and adaptable to many tasks. And transformers use a mechanism called attention to weigh relationships in data efficiently. A few more matter for risk. Natural language processing lets computers understand and generate human language. and sentiment analysis uses it to judge whether text is positive, negative, or neutral. Underfitting means a model is too simple to capture the patterns, while overfitting means it memorized the training data, including the noise, and fails on anything new. And AI as a service lets organizations subscribe to AI tools in the cloud without seeing how the model was built, which is convenient but carries its own hidden risk. Let's bring it all together. AI contains machine learning, which contains deep learning, which contains generative AI. AI is categorized by function, from reactive machines to the theoretical self-aware, and by capability, from today's narrow AI to the hypothetical general and superintelligence. Models include generative, agentic, and predictive types, and machines learn through supervised, unsupervised, and reinforcement paradigms, often using neural networks and deep learning. And key terms like large language models, transformers, overfitting, and AI as a service complete the foundation. That was the biggest building block in this domain, and you now have the full map. Every important topic and idea from this session is covered in the multiple choice questions on RooCloud.com. Before you move on to the next session, work through the chapter-wise questions there, because this vocabulary underpins everything that follows. Practice first, and then move forward with confidence. Thank you for watching, and I will see you in the next episode.